Welcome everyone. In this video we will find the acceleration of a ring rolling without slipping on an inclined plane. So let me draw the incline for you. Here is the inclined plane. This is 90 degrees. And let's say that the angle of inclination, it is an angle, it's theta. And there is as I said, a ring with mass m and radius r. So this is the radius and that's r. Oops, sorry. And we're told that this ring is rolling without slipping. So what is the acceleration of this ring? And when we say the acceleration of the ring, what we actually mean is the acceleration of the center of mass. And let's say that this is a uniform ring. So the center of mass is at the middle. And it will be accelerating with a center of mass, which we will just call A. So what is this acceleration in terms of given quantities? Well, to start off, we will of course draw the free body diagram as we do in most of the mechanics problem, if not all of the mechanics problem. There is the mg downwards. There is a normal force upwards. And since we're told that this is a rolling without slipping question, we're told by the question that the ring rolls without slipping, there must be a friction force. And that friction force will be upwards. Because otherwise, think about it. Let's say that you are walking on ice. You will probably slip, right? And why is that? Because there is little friction. And so if the ring is going to slip, if it is going to roll without slipping, then there should be a friction that is preventing it from slipping, all right? So that's how we know that there is friction. And this direction, if we draw it, this will be theta. So what would you do? You would first choose a coordinate system, hopefully. And the classic one in this kind of a situation is this one. And now we're ready to write the force equations. Let's start with the y direction. There won't be any acceleration in the y, so the forces should be equal. They are in opposite directions and they should be equal. So n will equal the y component of mg, which is mg cosine of theta. What about x? X will be, we will have mg sine of theta minus the force of friction, and this will be equal to ma. And as you can see from the x equation, what we're looking for is the frictional force. And please, 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 do not simply say, oh, F is equal to mu times n, and I know what n is, and maybe I'm given mu, maybe not. But please don't do this. First of all, I didn't give you mu in this case. I didn't give you the coefficient of friction. But more importantly, even if I did give it to you, it would be wrong. It might be right, but probably it will be wrong. Because this friction is not a kinetic friction. And that's why it is not equal to this. The friction that we're talking here is a static friction. It's a friction that is static. Static friction it is. And so this equality is wrong for static friction. It looks like this. There is a maximum value. And we have no idea whatsoever that the friction here is the maximum friction. It doesn't have to be. It doesn't have to be that, okay? So please don't make this assumption. It would be wrong. It would very, very probably be wrong. So yeah, what I'm trying to tell is, if you do this and you get the problem right, you were lucky. You were flat out lucky, okay? You were lucky. And also, you might be saying, why is this static friction? The ball is rolling. Well, the reason for that is, and we can discuss this in more detail in future videos, but the reason is the contact point between the ring and the surface, that point is stationary. The instantaneous velocity at that point is zero, and that's why there is static friction. But as I said, we can discuss this in further detail in future videos. What is the takeaway though from this 1.5 minute discussion? Don't do this mistake. Okay, we can't substitute for the frictional force, but we will find a way to have an expression for it. Don't worry. Let me erase that part. And let's even mention that this is a static friction. Okay, we made that discussion. This is a static friction. And I mean, if you look at this, this is not enough. We need one more equation somehow from somewhere. And that equation comes from the torque. We wrote the force, why not write the torque? And we know that this is the torque version of Newton's second law. We know that tau, the net torque, equals the moment of inertia times the angular acceleration. And we will be calculating the angular acceleration relative to the center of mass of the disk, because it's the easiest option here. And so when we do that, we will have hold on a second. So N and mg, they will be providing no torque because they pass through the center of mass. We are doing the center of mass calculation here. So the only torque can come from the static friction. And since it is tangent to the ring, it is along the path. That's why it is tangent to the ring. It is perpendicular to the radius. And since radius is the moment arm here, sine of 90 gives you 1. So the torque by the force of static friction is the magnitude of the force times the radius. This will equal the moment of inertia of the ring, that is mr squared. This is very easy to prove, and if you want, we can prove this in a future video, but for now, just take it for granted. But as I said, we can prove this. This is in fact very easy to show. And for the angular acceleration, since this is rolling without slipping, the question told us this. This directly means that A is equal to alpha r. This is literally the meaning of rolling without slipping. I guess you could even put an arrow this direction. I guess that this is a biconditional statement. I am pretty sure, okay? But if I'm wrong, please, correct me, but I really think that this should be a biconditional. But in any case, if it is a rolling without slipping, I can guarantee you that the question is telling you that A is equal to alpha times r, okay? So we can substitute that for alpha. Alpha, we will substitute A over r. Let me do it here, A over r. And look at this. All of the r's simplify. We see that the force of static friction is equal to mass times the acceleration. We can substitute it here. And when we do that, what happens? We have mg sine of theta. Let's just toss the static friction to the other side. So we have 2ma. The masses simplify. That's pretty common, I guess. So the acceleration is g sine of theta over 2. This is, as I was saying, the acceleration of the center of mass, because this is center of mass, and even here, that is center of mass. But, since I already mentioned it here, I hope that there isn't any confusion. But we just did it. We found the acceleration of the center of mass for a ring rolling without slipping on an incline. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. If you want to see future videos like this, please make sure to subscribe, and I hope to see you in another video. Until then, take care.